Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a final video on the mean value theorem and Rolle's theorem in a Calculus 1 course. This video covers what I think are the most important ideas out of this section that have true significance for the rest of calculus. And so we're going to start with something that's not named, at least in the book that I use, but I think is probably one of the more important uses of the mean value theorem for derivatives. And it's called, in some circles, the racetrack principle. You suppose you are given two functions that are continuous on a closed interval a to b and differentiable on the open interval from a to b, which implies we can use the mean value theorem with both of them. And we're going to assume that f of a is equal to g at a, and that f prime of x is always less than or equal to g prime of x on that given interval. Then our result of this theorem is that f of x must be less than or equal to g of x on the entire interval. Now, let me just describe this visually. So you have continuous and differentiable functions. And let's talk in terms of horses on a racetrack. And no horses were abused in this entire derivation. So this is not the proof. I'm just going to write it in the area of the proof, but I'll erase it when I'm done. So you have this racetrack. And this racetrack, sorry, that was not supposed to be like that. This racetrack starts at A and ends at B. Now, I'm not actually graphing these functions. Instead, I'm pretending as though there are horses on this track. So you have a horse called F, and you have a horse called G. Their positions, if we consider this way a position, their positions, they're head to head right at the beginning. So at the beginning, they're at the same position. This is not an XY axis, this is a top-down view. So the horses start moving and racing, but initially at time A, they have the same position. But horse F is slower than horse G. F prime is less than or equal to G prime. So in a few seconds, it should make sense that horse G is slightly ahead of horse F, because horse G is at the same speed, if not a little bit faster than horse F. And so therefore, for the rest of the race, if that inequality still holds, horse G is faster than horse F, then for the rest of the race, horse G is going to be in front of horse F because it's horse F is always slower. So that's why we get g of x is always ahead of f of x on that entire interval. So again, here's a theorem in calculus that if you read it properly, it's a pretty easy theorem to understand. You've got two things, they start at the same point, one thing is faster than the other, therefore the faster thing is always ahead. There you go, that's the racetrack principle. Its use, though, is pretty awesome. But we're first going to start just by proving this theorem, and then I'll showcase the use of it. For the proof, we're going to assume all the antecedents. So basically everything we're in the if part of the statement. That's quite a bit, actually. We have a pair of continuous functions, or functions that are continuous on a closed interval, and that are also differentiable on the open interval a to b. We're also going to suppose the functions are the same at a, so f of a is g of a, and that f prime of x is less than or equal to g prime of x for all x in the open interval from a to b. Now, this proof takes advantage of a tactic that's used throughout mathematics. We're going to let a function, since we're using f and g, I'll call it h. We're going to let h of x equal, let's do it in this order, f of x minus g of x. Okay. It's just a tactic where you glue your functions together because it's kind of useful. So note, this implies that h of a is equal to f of a minus g of a which is equal to 0 because f of a is equal to g of a. Now, the thing we need to assume here, or not assume, but the thing that we can use here is the fact that f and g are continuous on the closed interval from a to b and differentiable on the open interval. That means that h is also adopts those qualities because it's just a difference of f and g, so it adopts all those conditions from f and g. And we mention this because we're going to use the mean value theorem. However, I'm going to use the mean value theorem in a slightly different way. I hope you'll agree with me that if h is continuous on the interval, closed interval from a to b, and differentiable on the open interval from a to b, that it's continuous on any sub-interval from a to b and any differentiable on any sub-interval from a to b. That is, h is continuous on the closed interval a to some number b hat, and it's differentiable on the open interval a to that same number b hat, where b hat is between a and b. This is an adjustment that I make to this proof because I dislike the way this is normally proven, and I think it's better to say it this way. So I'm really going to do the rest of my proof based upon some arbitrary number, and that's critical to note, that b hat here is an arbitrary number between a and b. We need that for our proof to really work. And because we have those two conditions met, we can use the mean value theorem on those subintervals. So there exists a c in the interval a to b hat, open interval that is, such that, let's see, h at c is equal to h at b hat minus h at a over b hat minus a. And what I'm going to do is multiply both sides to get it in the alternate form. So this is h prime at c times b, again hat, minus a, is equal to h at b, again hat, minus h at a. And I'm going to use something that we mentioned a little bit earlier. H of a, looking at this part right here, h of a is just going to be 0. So I'm going to replace that h of a with 0, so we get h of b hat is just equal to h prime of c times b hat minus a. I'm actually going to write it in the opposite order because it's kind of nice to do that for this proof. So I'm going to say this implies that h of b hat is equal to h prime at c times b hat minus a. Now there's a couple things I need to kind of draw your attention to here. H prime at c, well, h prime is equal to f prime minus g prime. And we already know that f prime is less than or equal to g prime for all x in our interval, a to b. But that interval from a to b hat is a subinterval, so again, that inequality still holds. It's actually less than or equal to technically. And so that implies that h prime is less than or equal to 0 for all x in the interval from a to b. Well, that means that this h prime of c, because c is in between a and b, that h prime of c is negative or 0. B minus a, well, b is in front of a, right? B hat, sorry. B hat is greater than a, so b hat minus a is positive. And we have some positive number times some negative or 0 number. That will imply that h of b hat must be less than or equal to 0. Again, because h of b hat is a negative or 0 number times a positive number. So it's less than or equal to 0. But remember what h is. H is f minus g. So f of b hat minus g of b hat is less than or equal to 0. Or in other words, f of b hat is less than or equal to g of b hat. What have we proven? We've proven that based upon the initial assumptions that f and g are continuous on the closed interval from a to b and differentiable on the open interval from a to b, and that f of a is equal to g of a and f prime of x is less than or equal to g prime of x for all x in the open interval, we've proven then that for any number between a and b, that's that highlighted b hat here, any number between a and b, f at that number will be less than or equal to g at that number. And therefore, f of x must be less than or equal to g of x on the interval. So we are done. QED. And here's where you're actually going to use the racetrack principle. Problems like these, where you want to showcase that one function is less than or equal to another function on an interval. This gets used throughout a lot of mathematics. And so knowing the racetrack principle is really powerful. Now, I'm taking an example where these two functions are the same rather than convoluting this. I should say the same at the beginning. So when x equals 0, they have the same value. I was going to have an example, it's underneath here, where they're not the same initially, but I think that would convolute the argument. So instead, I'm going to focus just on them having the same initial value. So here's how you do this. You're going to let f of x equal x plus 1 and g of x equal e to the x. Now, to use the racetrack principle, it's like the mean value theorem, because you had to use the mean value theorem to prove it. So you need these functions to be continuous and differentiable. Well, f and g are continuous and differentiable on the real numbers. So I'm just going to write it this way: continuous and differentiable on the real number system. That's the first condition to start using the racetrack principle, that they are continuous and differentiable, because you're using actually the mean value theorem in here. The second condition is that you need their initial values to be the same. Technically, you could have the faster function have a larger initial value, but we're just going to do it this way. So this implies f of 0 is equal to g of 0. So that's the second condition. The third condition, f prime of x is 1 and g prime of x is equal to e to the x. Now, this is greater than or equal to 1 for all x greater than or equal to 0. G prime of x is just a function evaluation at that point. So g prime of x definitely is greater than or equal to 1 for all. It's an increasing function, and at 0, it is 1. All right. So this implies that f prime of x is less than or equal to, because it's 1, it's less than or equal to g prime of x for all x greater than or equal to 0. So we have those three conditions met. We have continuity and differentiability. We have the two functions are equivalent at the beginning, although the faster function, g, could be slightly ahead. We would be okay with that. I just didn't want to use that example here. And then you have this showcasing that one function's slower than the other. So f prime is 1, g prime is e to the x, which is greater than or equal to that 1. So g prime is greater than or equal to f prime. This immediately means that by the racetrack principle, that f of x is less than or equal to g of x for all x greater than or equal to 0 by, again, the racetrack principle. Racetrack principle. I'll just do it that way. And what was f again? Oh yeah, that's right. F was x plus 1 and g was e to the x for all x greater than or equal to 0. That's a great use of the racetrack principle. Often you're faced with functions or inequalities involving functions where you're like, I don't know if that's actually true. Is the square root of this greater than that? racetrack principle is it comes to the rescue. So I highly recommend you spend some time looking for problems involving the racetrack principle, inequalities of functions, and just try to prove it. By the way, again, I just want to repeat this. At time 0, or whatever the time interval starts for your functions, it's okay for the faster function to actually start slightly ahead. Let's just pretend that this started at 2 and that started at 1. That's totally okay. It's a faster function. If it starts ahead, then it'll still finish ahead. What you don't want is for the faster function to start behind, because then the racetrack principle can't be used. All right, so that's a good example of the racetrack principle. Now we get into some consequences of the mean value theorem for derivatives that really lead us into Calc 2, honestly. So the first one, both of these are very easy to understand. If your function has a derivative that's 0 for all values on an interval, then it's a constant function. That should be pretty darn obvious. Let's go ahead and prove it. I just need to zoom in. So supposing that f prime is equal to 0 for all x in our interval from a to b is a good start. I actually want to use the mean value theorem here, but unfortunately, differentiability on this open interval does not imply continuity on the closed interval. So it implies continuity on the open interval, yes, but not at the edges. So what I'm going to do is a slight modification here. We're going to take two numbers within that open interval where a hat is less than b hat. And because those numbers are within the open interval, we know the function is differentiable between a hat and b hat. But we also know, because differentiability implies continuity, we know our function is differentiable from a to b, which means it's continuous everywhere in here. Specifically, if I grab 2 points, a hat and b hat, it'll be continuous between and including the edges at a hat and b hat. So that is how we're going to sneak the mean value theorem in on this. And there we go. But this implies there's some number between a hat and b hat such that the derivative of f at that number is equal to the slope of the secant line. So let's go ahead and write that down. And that is by the mean value theorem. So I'm just going to put that off to the side, mean value theorem. Okay, and I'll put it in its alternate form. Notice that I don't start with the alternate form, but I often just manipulate to the alternate form. And that's just because I don't like to memorize a ton of little forms here. And the slope of a line we've dealt with for so many years that's just so much easier to write down and remember. So, and if I don't screw up my handwriting, that'd be awesome. There we go. However, we made an assumption. Our assumption was that f prime of x is equal to 0 for all x between a and b. So this f prime of c must be 0. So that implies 0 must equal f at b hat minus f at a hat, which implies f of b hat equals f of a hat, or vice versa if you want to write it that way. Since a and b were arbitrary, let me write that down. Not a and b, but since a hat and b hat were arbitrary, then all function values for f are the same on a to b. Again, a hat and b hat were just random numbers we grabbed out of the bucket of numbers from a to b. And those randomly grabbed numbers end up being the same value. That means any two numbers we would grab from there would be the same value. That means that the function is constant throughout that entire interval. So that implies f is constant, again, on the open interval from a to b. QED. All right. Very, very nice, clean proof. That actually doesn't, I mean, yes, it gets used just naturally. We just know if a function's derivative is 0 for all x in an interval, then the function's constant on that interval. That's not the important one. The next one is the important one. We just needed this for the next one. And here is the proof, or the theorem, sorry, that leads to Calc 2. So if f prime is equal to g prime for all x in an interval, then f minus g is constant on that interval. Okay, that I don't even really truthfully need to prove that, because if I told you f prime is equal to g prime on an interval, then you could say, well, let h equal f minus g, then h prime is equal to f prime minus g prime, and that is 0 for all x in that interval, which implies, we'll see, I'm already doing the proof, h is constant on that interval from the last theorem, which implies h equals some constant k, which implies that constant k is equal to f minus g, or in other words, that f is equal to g of x plus some constant k. I actually just proved the whole silly theorem, right? So if you have two functions whose derivatives are the same, this is the kicker here. You have two functions, derivatives are identical. Then one function is just a constant added, or a shifted version, a vertical shift of the other function. So f of x is just g of x plus c, or vice versa. G of x is f of x plus c. That plus c is going to be kind of important for us in Calc 2. So how does this get used? I'm going to do something that I find super entertaining. I am going to go back to trig. Remember all of those trig identities you had to prove in your trig class? Well, guess what you can do? You can prove them using calculus. For example, here's a really common theorem we all know. Sine squared of theta plus cosine squared of theta is equal to 1. We all know that, right? That's the Pythagorean identity from trigonometry. What you can do via this theorem is you can take the derivative of both sides. So if I say, well, f is equal to sine squared of theta plus cosine squared of theta, and g is equal to 1, then f prime of theta is 2 sine of theta cosine of theta by the chain rule minus 2 cosine of theta times sine of theta. The minus comes from the fact that the derivative of the cosine of theta is a negative sine of theta. And this is 0, isn't it? We can see the g prime is 0 because g is 1. So this tells us that f must equal g plus a constant c. That's a capital C. That's how I do my capital C's. This implies that sine squared of theta plus cosine squared of theta, that's f, must equal g, which is 1, plus some constant c. Now all you need to do is intelligently select an appropriate value for theta, like theta equals 0. Because this equation is true, this is called an identity, this equation is true. We just say like, okay, well then this equation is true by the previous theorem. If their derivatives are the same, then these functions just differ by a constant. If you want to find that constant, let theta be any number you want. Specifically 0 is very nice. So if you do that, you'll get 0 plus 1 is equal to 1 plus c, or in other words, c is equal to 0. So therefore, this proves if c is 0, that sine squared of theta plus cosine squared of theta is equal to 1. So it's interesting, you do all those proofs in trigonometry, and they're kind of, I enjoyed them. I think they're great proofs, but turns out once you hit calculus and you get to these theorems that you can actually prove them a different way using derivatives. So let's prove one that we wouldn't have been able to really prove very easily in a trig class. Let's prove that twice the sine inverse of x is equal to the cosine inverse of 1 minus 2x squared for x greater than or equal to 0. So let's go ahead and see what happens here. Now there's a subtlety here. There's actually a secondary limit on that x, but I'm not going to really worry about that. doesn't actually matter with this proof, but the secondary condition is that x has an upper bound as well, because the cosine inverse will never return anything, or will never accept anything greater than 1. So don't worry about that too much. All right, so let's go ahead and prove this identity. We're going to let f of x equal twice the sine inverse of x. And g of x, I'll write it off to the side here. We're going to let that equal cosine inverse, or the arc cos, of 1 minus 2x squared. Taking the derivative of each of these, so f prime of x is twice 1 over the square root of 1 minus x squared. And g prime of x, if you don't remember the derivative of the cosine inverse, it's a negative derivative of the sine inverse. So it's going to be a negative derivative of the sine inverse, which is 1 over the square root of 1 minus the argument of the cosine inverse squared. 1 minus 2x squared squared. And then by the chain rule, we're going to go ahead and take the derivative of the argument of the cosine inverse there. That'll give us a negative 4x. Now, obviously, these do not look the same, at least at first, but we're going to manipulate here. Negative times negative will get me a positive 4x in the numerator. In the denominator here, we'll get a 1 minus 1 plus 4x squared, and then, what is that, a minus 4x to the fourth? Okay. And let's see how this simplifies down. That's a 4x over the square root of 4x squared minus 4x to the fourth. And here's where the condition on, I'm going to factor 4 out and take the square root, so we get 2x over square root of x squared times the quantity 1 minus x squared. I'm going to leave it like that for a moment. This is where the condition that x has to be greater than or equal to 0 comes into play. Obviously, it can't equal 0, but it can be greater than or equal to 0. So the square root of x squared normally is the absolute value of x. That's going to become critical in Calc 2. But in this case, because we already know that x is greater than or possibly equal to 0, although it can't be equal to 0, all right? But we know it's greater than 0 or positive, then we don't need the absolute value signs. So this is the same thing as 2x over x root 1 minus x squared. The x's cancel, and you get this as 2 over root 1 minus x squared. Notice that derivative is the same as f prime. So f prime and g prime are the same. Since f prime is equal to g prime, we know that f is equal to g plus some constant c. That is 2 sine inverse of x must be equal to cosine inverse of 1 minus 2x squared plus some constant c. They're just off by a constant. Now what do? Well, you make a decent choice for x to substitute in. Rather than having the conversation that x, I could sub in x equals 0, but the problem with that is that in my derivative, you could see division by 0 is a no-no. So I am sort of going to hand wave that and just choose x equals 1 over root 2. You could choose any x value, but I'm choosing x equals 1 over root 2. So I'm going to say let x equal 1 over the square root of 2. And you'll get 2 sine inverse of 1 over root 2 is equal to the cosine inverse of 1 minus 2 times 1 over root 2 squared, which is times 1/2, plus c. All right, so far so good. Well, that's 2. The sine inverse of 1 over root 2 is actually, it's the same thing as asking what would you plug in the sine to get 1 over root 2? That's a pi over 4. The cosine inverse, well, we're dealing with the cosine inverse of 0. The cosine inverse of 0 is pi over 2. So we get pi over 2 is equal to pi over 2 plus c. Or in other words, C is 0. Well, since C is 0, we have proven that these two functions, 2 sine inverse, sine, not secant, sine inverse of x is equal to cosine inverse of 1 minus 2x squared. A really cool way of doing a trig proof. Highly recommend it. All right, that finishes out the series of videos on the mean value theorem. I hope you enjoyed.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.